Hello everyone. Today we are discussing about Euler's formula. Euler's formula is a connected planar graph with V vertices and E edges has E minus V plus 2 number of regions. Mathematically, this can be written as R is equal to E minus V plus 2, or we can rewrite the same equation as R minus E plus V is equal to 2. So we are proving this Euler's formula by the method of mathematical induction. So for that, first of all, consider a planar graph G with V vertices and E edges. So the theorem can be proved by constructing a sequence of subgraphs, say G1, G2, G3, etc. up to GE. So that can be constructed by successively adding an edge at each stage. So we can say we are proving Euler's formulae by mathematical induction. So for that we are considering subgraphs. Initially we are considering a graph without any edge. Let it be denoted as G1, and during the next phase we are considering a graph by adding exactly one edge towards G1, let it be denoted as G2, and the process is repeated. Okay, so for simplicity we are considering a graph Gn where Rn represents the number of regions of that graph, say Gn, En represents the number of edges of that graph, and Vn represents the number of vertices of that graph in Gn. We know mathematical induction involves basic steps as well as inductive steps. So we have to prove the entire theorem using mathematical induction. But then that basic step says we can prove that the given Euler's formula is true for the initial value of n. That means n equal to 0, n equal to 1, n equal to 2, etc. We have to prove our theorem is true. So for that, first of all, we are taking say n equal to 0. That means we are assuming a graph with 0 edges. That is the assumption when n equal to 0. So you have to consider a graph, say G1, with a single vertex and no edge, and that can be represented in a figure like this. G1 is a graph with exactly one vertex without any edges. So by default we know if a graph that is only one vertex without any edges is only exactly one infinite region or outer region. So based on our graph G1, the number of vertices V1 is 1, number of edges E1 is 0, and number of regions R1 is also 1. So while applying the Euler's formula for G1, R1 is equal to E1 minus V1 plus 2, and substitute the values of edges, vertices as well as regions. 1 is equal to 0 minus 1 plus 2, that is equal to 1, means 1 equal to 1, which is always true. So we can say the relation R1 equal to E1 minus V1 plus 2 is true for n equal to 0. That means for graph G1. Now we have to prove for n equal to 1 also our equation is true. That means we already see in each step we are successively constructing a graph by adding exactly one edge towards the previous graph. So previously we have considered G1 as the graph without any edges, and now we are considering graph G2 with two vertices and exactly one edge, and it can be represented in this figure G2. G2 has two vertices, say V1 and V2, and these two vertices are connected with exactly one edge, say E2. So here we can say number of vertices is 2, number of edges is 1, and again number of regions in G2 is exactly 1 infinite or outer region. Now apply our Euler's formula towards this graph, say G2. Our Euler's formula is R2 is equal to E2 minus V2 plus 2. So R2 means regions in G2, that is 1 is equal to 1 minus 2 plus 2 is again equal to 1, which is always true. So we can say the relation R2 equal to E2 minus V2 plus 2 is true for n equal to 1. That means for our graph CG2. And similarly, for n equal to 2, that means we are considering graph G3 by adding one more edge towards G2. That means we have considered G3 as a graph with 3 vertices and 2 edges. Again, while evaluating this G3, we can see that there is exactly one outer or infinite region. So based on G3, the number of vertices, say V3 is 3, and number of edges in G3, say E3 is again 2, and number of regions in G3 is 1. So again, consider the equation, Euler's equation, R3 is equal to E3 minus V3 plus 2. Substitute the values. R3 is 1. 1 is equal to 2 minus 3 plus 2. 1 is equal to 1, which is again true. Therefore, we can say the relation R2 is equal to E3 minus V3 plus 2 is true for n equal to 2. That means it is true for a graph, say G3. So these are the basic steps. Now we are moving towards the inductive step. We have to prove the inductive step. That is, assume the equation is true for n equal to k. That is, Euler's formula is true for n equal to k. That is, Rk is equal to Ek minus Vk plus 2 is true. We are assuming like that for a graph Gk, and we have to prove the above equation is true for n equal to k plus 1. Means for a graph Gk plus 1, we have to prove this is always true. That is, Rk plus 1 equal to Ek plus 1 minus Vk plus 1 plus 2 is true. We have to prove based on the assumption that we are assuming what this equation is true for n equal to k. So while evaluating these two, we can see that first of all, we are assuming that our equation is true for n equal to k. That is for a graph Gk, and towards that graph Gk, we are adding one extra edge in order to obtain the second graph. What is it? Gk plus 1. So let's assume we are adding an edge. Let it be denoted as its end vertices of that edge can be denoted as Ak plus 1, Bk plus 1. So we are assuming this is an edge that is to be added towards Gk in order to obtain Gk plus 1. So our assumption is we have to prove our equation is true for n equal to k plus 1. So while we are considering addition of an edge with end vertices Ak plus 1, Bk plus 1 towards Gk to obtain Gk plus 1 graph, there are mainly two possibilities. One is both the end vertices of this newly added edges are already in Gk. Otherwise, one of the end vertex of this new edge that is to be added as Gk, another end vertex is not in Gk. These are the two possible cases. So we will study about these two cases separately. So just consider the first case. Both the end vertices of the newly added edge, say Ak plus 1 and Bk plus 1 are already in Gk. So these two vertices must be on the same boundary of a common region, say R, or else it would be impossible to add an edge like this towards Gk without edge crossover. So if there exists any edge crossover, so our graph will become non-planar. So we are always considering the graph is always a planar graph for Euler's formulae. So if we are considering two end vertices and of a newly added edge, and these two end vertices are in the same graph, so we can say these two end vertices are the boundary of a common region. Otherwise, if these two end vertices are not the boundaries of a common region, and if we are adding an edge between these two end vertices, that edge will cross any other edge, so that the graph is not planar. So our assumption is graph is always planar. So we can say these two end vertices are always the boundaries of a common region, say R. So addition of this new edge split R into two regions. So this can be represented in the form of a picture in the next slide. So just consider GK graph with 4 vertices, and our first case is what? That means if we are adding a new edge whose both the end vertices are in the same graph, say GK. So let's assume the end vertices as AK plus 1 as well as BK plus 1, and if we are adding an edge between these two end vertices, we have to obtain one more region. Okay, so while adding a new edge towards GK, we are obtaining another graph. Let it be denoted as GK plus 1. So I think the concept is clear. Now consequently, if we are considering the graph GK plus 1, that means we are adding an additional edge towards GK, we are obtaining a graph GK plus 1. And considering GK plus 1, what about the number of regions? So if GK has RK number of regions, in GK plus 1, there is RK plus 1 number of regions. So in our graph GK plus 1, the number of regions that can be denoted as RK plus 1, that is always equal to number of regions in GK. What is it? RK plus one more region. Okay. Similarly, in this graph GK plus 1, number of edges. What about the number of edges in GK plus 1? Let it be denoted as EK plus 1. So the number of edges in GK plus 1 is what are all the different edges that happen that will be available in GK plus one more additional edge. So we can say the number of edges in GK plus 1 is EK, that is number of edges in GK plus one more edge. That can be represented like this. Similarly, what about the number of vertices in GK plus 1? The number of vertices in GK plus 1 can be denoted as VK plus 1. That is equal to the number of vertices, the same number of vertices in GK. We are not at all adding any additional vertex towards GK in order to obtain GK plus 1. So number of vertices in GK plus 1 is the same as number of vertices in GK, that is equal to VK. Okay, so now based on the Euler's formula, we can write the Euler's formula for the graph GK plus 1 is RK plus 1 equal to EK plus 1 minus VK plus 1 plus 2. So what's the value of RK plus 1? RK plus 1 is RK plus 1 is equal to, what's the value of EK plus 1? EK plus 1 is EK plus 1 minus VK plus 1 is the same as VK plus 2. So in both the LHS as well as the RHS contains 1, we can cancel both this 1, so that this equation becomes RK equal to EK minus VK plus 2. What is this? This is already always true. That is our assumption. So which is always true. Therefore, we can say what our assumption is also true. That is RK plus 1 equal to EK plus 1 minus VK plus 2 is true. That means from this equation, we are obtained this equation. Okay. And this is already true. We are assuming that this is already true. Therefore, we can say this equation is also true. Okay, now we'll move on to this next case. That is one of the two vertices of the new edge is not already in GK. So our first case is we are assuming that both the end vertices of the newly added edges in GK. And now second case is one of the end vertex of the newly added edge is not in GK. That can be represented like this in this figure. You just consider this figure. So this is our GK, and in GK, one of the end vertex can be represented as AK plus 1, and towards this GK, we are adding a new edge with the property that addition of this edge whose one of the end vertex is not in GK. So this is our GK plus 1. So while considering this new edge whose one end vertex is in GK, another end vertex is in not in GK. So this is our newly added edge resulting graph is gk plus 1. And based on this graph gk plus 1, we can find out the number of regions, number of edges, as well as number of vertices. So number of regions of this gk plus 1 can be denoted as rk plus 1. And if we are adding an edge like this, doesn't affect the number of regions as in previous graph, say gk. So the number of regions in gk as well as gk plus 1 is the same. So rk plus 1 is the same as rk. Then what about the number of vertices in gk? Let it be number of vertices as vk, and in gk plus 1 number of vertices is plus 1. So vk plus 1 can be represented as vk plus 1. And what about the number of edges of gk plus 1? We are adding a new edge. So number of edges can be denoted as ek plus 1, that is equal to ek, that is number of edges in gk plus 1. Okay. Now Euler's formula for the graph gk plus 1 can be represented as rk plus 1 equal to ek plus 1 minus vk plus 1 plus 2. Now substitute the values. Rk plus 1 is rk itself, that is equal to ek plus 1 is what? Ek plus 1 minus of vk plus 1. What's the value of vk plus 1? Vk plus 1 minus of vk plus 1 plus 2. Now expand this equation. This equation is the same as rk is equal to ek plus 1 minus vk minus 1 plus 2. So in RHS there is a plus 1 as well as minus 1. We can cancel both of these terms. So the resultant equation is rk equal to ek minus vk plus 2. This is always true. We already assume that this is true. So from this equation, we are obtained this equation and this is true. Therefore, we can say our assumption. What is it? Rk plus 1 equal to Ek plus 1 minus Vk plus 1 plus 2 is true. Hence, Euler's formula is true for all planar graphs. Okay. This is the proof by the method of mathematical induction. And one more doubt that comes while we are discussing about this, we are only considering two cases. Case one is what? If we are adding a new edge whose both the end vertices are of the graph GK itself. Second case is one of its end vertex is in GK and another end vertex is not in GK. And now, why we are not considering a graph with both of its a graph with addition of a new edge whose both of the end vertices are not in GK? What happens if both the end vertices of a newly added edge towards a graph GK that are not in GK? What happens? That we can say that graph becomes disconnected. A connected component GK as well as another component with exactly one edge with its end vertices as AK plus 1 as well as BK plus 1. So we are not considering disconnected graphs, we are considering only connected graph. That's why we are not taking that case. Okay. So these are the two cases. I think all of you clear about this Euler's formula. Okay.